All right, hi everybody. Welcome to our last section that we'll be looking at for Chapter 7 in this module, 7.4, where we're going to be estimating the differences in population means and the differences in population proportions. Okay, so everything that we've been doing up to this point, we've been comparing a sample statistic to a population parameter. And here we're going to be looking at if there's like the techniques that we can use to compare two different populations. Okay. And the first thing that I sort of want to mention is a little bit, I guess, off topic. It'll be a little bit more relevant as we go into further chapters. But I wanted to go over this idea of a student's t-distribution and then also compare that to our normal distribution, okay? So a student's t-distribution is going to be a derivation from the normal distribution. And basically the way that it was derived, that's supposed to be, it's a little bit more of a lax normal distribution. We don't have to have as many criteria or criteria that need to be met to use this student's t-distribution. And its biggest application is that the student's t-distribution can be used for problems where only statistics, such as sample numeric characteristics, are known. Okay? And up to this point, we've really been focusing on like normal distributions and like the sample size having to be greater than 30, and it's like following this kind of like normal distribution pattern. A lot of that kind of characteristics get dropped when we talk about t-distributions, and we're only working with sample means, samples, standard deviations, and so on. Okay, and calculations related to students' t-distribution are going to be later. You might see some kind of problems where they talk about students' t-distribution, so I wanted to give you a quick introduction to that here. Okay. After that aside, let's go into the meat of chapter 7.4, or the section of 7.4, where we're going to be computing the confidence intervals, and we're going to be looking at the comparison of two means, okay? And in these problems, we're going to be given the population standard deviations as well as the sample means. Okay, so here when we're comparing two different sample means in general, we want to figure out if our samples are independent or dependent, okay? And this brings us to our first couple definitions for this chapter of how can we define if two samples are independent from each other or dependent from each other. Well, two samples are independent from each other if the samples are completely unrelated to each other in nature and how they were taken. So, in other words, the data points from one sample cannot correspond with the data points in another sample. And here we have an example of that. If we take the blood samples of vitamin D patients and some people in Cleveland, Ohio, and then we take blood samples and look at the vitamin D levels for people in Tampa, Florida, and we're comparing those two samples, okay? The people in these studies are completely unrelated, and we can sort of get that vibe too. Like the first part is that we have like the populations like patients in Cleveland, Ohio, and the second population is patients in Tampa, Florida. Those don't even sound like the same populations. So because these are unrelated, we can think about these samples as independent. Okay. The flip side is that the dependent samples are going to be related to each other, where you can correspond a data point for every single point on one sample over to another. Okay, so an example of that is when you take blood samples from vitamin D patients from some people in Cleveland, and then let's say we take the samples 12 weeks later after giving them a course of vitamin D tablets. Okay, the data points from the first time the vitamin D samples were taken can directly correspond to the sample sizes that are found, the sample data points that are found in the second sample, okay, the data points in the second sample, because we can correlate the first blood sample that we did for patient 1, for example, and compare it directly and correspond it to the blood sample that they have after that person has after 12 weeks from that tablet. So because all of these data points can be sub-tagged together in a very logical manner, these samples are dependent, okay? And it's very important to be able to define independent and dependent, because in these techniques that we're going to be talking about, only independent samples can be compared in these techniques. Okay, so if you have dependent, there's different techniques that you can use, and we're not going to be getting into them in this course. They're going to be outside of the scope. Okay, so we're only going to be working with independent samples here. Okay, but it's good to get into the habit of identifying those. Okay. So now that we have those definitions out from the side, we can now try to find the confidence intervals for the difference between the two population means. And as we potentially suspect, because we're looking for a difference between the population means, we're going to be taking a difference from the sample means. In other words, we're going to be subtracting the sample means in some way, okay? And as we talked about with all of our confidence intervals, to create those boundaries, we're going to have to use that maximal margin of error again, okay? So rewritten, we're going to be, we see that our confidence interval is going to be whatever our difference of means are, and we're going to add or subtract them from our margin of error to get those boundaries, okay? And here we define the margin of error in this equation that I'm highlighting in green. We're going to be taking our z critical value. So here we're working with z. We're not even talking about the t-distribution, the student's t-distribution that we talked about earlier. And we're going to be multiplying that z critical value to the summation of our population standard deviation for our first sample squared over that sample size for the first sample that's taken, and adding that to, or the sum of, basically, the squared value of our second population standard deviation divided by that sample size as well. And then after that summation is taken, you're going to take the square root of it, okay? So that's why I wanted to get us into the habit of writing out all of our variables as we move forward, because as we can see here, it can get really messy. We have 1, 2, 3, 4, 5 different variables that we're working with our maximal margin of error here, okay? So I'll reiterate this in the next video as well, but make sure you're writing out all of your variables as you go for these examples, okay? And now we're going to get into one of those examples.